Hello students, let's begin lesson 3b, exact equations. This topic requires some preliminaries, and section 0 of this notebook was taken from lesson 1a. And we covered this thoroughly there, so if there's anybody who skipped over that topic or did study but forgot about everything, you can always go back to lesson 1a and study there. So let's go over to section 1 of this notebook, and let's begin from the chain rule. Here's a chain rule in single variable calculus, and in calculus 1, I explain it in this way, in three-step process. Derivative of the outside first, and then inside stays the same, step 2, and step 3, multiply the derivative of the inside. So I do it in three-step process. But that's because it's Calc 1. I see so many mistakes from students that take the derivative and leaving it inside the parentheses. I wanted students to avoid that, so I singled out this red part and made it into a three-step process. But in reality, this is actually a two-step process. This is 3000 level course, so I don't think students will have much trouble about this red part here. So let me explain it in terms of a little bit higher level. So this is basically outside. Derivative of the outside times the derivative of the inside. That's basically it. That's blue, and that's green. Now keep this in mind, and let's go to chain rules in double variable calculus. It looks like this. Derivative of the outside function times the derivative of the inside function. Exactly the same thing repeats here. Now, what's the derivative of the outside function? That's harder one because capital F here is double variable function. So it has two variables, x and y. So we have two partial derivative, df dx and df dy, and those form the first component and the second component. How about the green part? X and y are two separate functions now, even though they're paired together, and they're both single variable functions. So x prime of t, y prime of t, you can calculate separately. You can consider x comma y as a position vector. Then its derivative is the rate of change, is the velocity. So this green part corresponds to velocity, and blue part corresponds to partial derivatives. By the way, pairing up partial derivative, what kind of vector is it? There's a name. It's called gradient. It's a gradient vector. How about the inside? Is the velocity vector. So the chain rule in double variable calculus is basically gradient times velocity. Previously, outside times inside. It's the same structure, but we have some more fancy name, gradient times velocity. We still have multiplication, but what kind of multiplication is it? Multiply two vectors. How do you do that? Multiply by each component. First component times first component. Second component times second component, and add them all up. In the end, we have scalar. It is called dot product or scalar product or inner product. And that's the chain rule. Now, what if we have more than two variables? Actually the same. We have the gradient vector, which is, well, a little bit more complicated this time. I have extra space there. We have n tuple of partial derivatives because we have n components. And then we have n tuple of total derivatives here because we have n components again. And then take the dot product, so multiply each components together and add them all up. And that's the chain rule. Again, we have gradient vector times velocity vector. That's about it. Okay, that's chain rule, and we have one more topic to go. That is second partial derivatives. How about the second derivatives? Well, there are more than one components, so there are more than one partial derivatives out there. So here's a question. In which order do you have to take it? Take the partial derivative by x first and then by y later, or vice versa, by y first and then by x later. Will that make any difference? Actually, no. It's called Claro's theorem, and if all the partial derivatives exist, all the second partial derivatives exist, and if all of them are continuous, then the order does not matter. You can do either way. Here in differential equations, just about every function we are dealing with are assumed to be differentiable infinitely many times, so you don't really have to worry about singular cases. You can take partial derivatives in any order. Please remember that, because we're going to be using it soon. Okay, let's go to exact differential equation. What do you mean by exact differential equation? It's a differential equation of this form with this condition. Let's go back to this and analyze. N dx plus n dy equal to 0. Or from here, divide everything by dx, and then what do you have here? M plus n dy dx equal to 0. Or you can write this one as y prime, just like the way our textbook author does. That's okay too. In this example, I'm using both notations. Here, my preferred notation with dx and dy separately, and our textbook author's notation, y prime here, or this could be rewritten as dy over dx. They're the same, but I prefer this notation here, and there's a reason. This notation here can be extended over to a little bit more general case where both x and y are functions and there's real independent variable t out there. Basically, I'm talking about this circumstance, this situation. Let me expand the font. And then dt, like this. From here, it's going to be a little bit more difficult to extend over. We need some more algebra and we need some more chain rule to do that. But from here, no problem at all. So I prefer this one. And also, theoretically, this one is going to be a little bit better and we're going to be using it. Pretty soon we will. I don't know whether we'll do it in this video or next video, I don't know, but pretty soon we'll use it. We're going to use this form soon. But in terms of problem solving, it does not matter whether you use this form or that form, it doesn't matter. As long as we have this condition here. Let's see, let's come back to this. What condition is this? Partial derivative of m by y is equal to partial derivative of n by x, or more simply, m sub y is equal to n sub x. If so, then we're going to call this equation exact. Why is this related to what I just talked about, to the chain rule? Well, I'm dying to go there, yeah, but let me slow down and let's do some exercises before that. Let's open up this exercise and let's check whether this equation is exact or not. In other words, let's check this. All right, ready? Here, m is, well, this is m. And this is n. So far so good. And let's check the partial derivative. Partial derivative of this one by y is equal to partial derivative of this one by x. Which notation do you prefer? Do you prefer these dm dy notation or m sub y notation? Me, my preference is this one. So I'll do it my way. So m sub y, from here, let's take the partial derivative by y. So let's take the partial derivative of this one by y. Is it 6x? No, if you take the derivative by x, then it is 6x, but by y, that's 0, because x is constant there. As far as y is concerned, x is constant. Now how about this one? Partial derivative of 4xy by y. 4x is coefficient, so this is what you're going to get. And then minus 2, well, of course, that's 0. So we have 4x. How about n sub x? From here, let's take the partial derivative by x. What do you have from the first term? What do you get from the second term? No x there, so that's y. So that's 0. So we have 4x again. Are they the same? Yes. So this equation is exact. How about the next problem here? This is m, and this is n, right? And then your job is to figure this one out. Are these two, are these two really the same? That's what you have to check. I'll leave this to the exercise. Well, how about some non-example? Okay, let's go to section 3 of this notebook. And it says non-exact ODEs made exact. So these examples must not be exact. Well, let's check. First problem. M is x times y. N is this one. What is m sub y? Take the partial derivative of this by y. What do you get? That's what I'm getting, right? X is a coefficient function. Now, how about n sub x? Take the partial derivative by x here. Take the derivative, and then I have 4x, and the others do not have any x in there. So they're all constants as far as x is concerned. So that's what we get. Are they the same? No, they're not the same. So this equation here is not exact. This problem says non-exact ODEs made exact, so these examples are going to be non-exact, but somehow you'll have to work those out and use appropriate method and make those into exact equation, and then you can go from there. But that's something we're going to discuss later. As for these two problems, they're coming from sections of the exact ODEs, so they're going to be exact. You can check those. And how do you check those? Well, we did this one, but this one I'm leaving to students. Okay, all right. So much for the preparation, and let's go to theory. I don't know whether I have enough time to do that. If so, I'll have to stop and then I'll resume in the next video. Okay. Basically, what we want is an implicit solution here. Capital F of x comma y is equal to c. That's what we want. Now, if there's a solution like that, what will that mean? If we have an implicit solution like this, then it is possible to take the derivative and we are going to get this. Oops. D And derivative of constant c is of course 0, and this is what I have to get. Okay, so far so good. We have to take the derivative here, and the derivative of the right hand side is of course 0 because this is constant. Now, what is derivative of this double variable function where x and y are also functions of t? Well, later on, I'm going to have to go down and then take the special case x is equal to t. But let's do it in a little bit more general setting because that's going to be necessary at this moment. Okay, so x is going to be a function of t. Y is going to be a function of t. So I'm taking the derivative like this. It's a chain rule. So we have to take the derivative of the outer function, partial derivative, times derivative of the inner function. And that had better be 0 because we know the right hand side will vanish because derivative of constant is 0. Does it make sense? Let me expand the font a little bit. And please recall the chain rule. This is the outside, that's the gradient, and then this is the inside, that's the velocity. Gradient times velocity is equal to 0. Vector times vector is a scalar because we are doing what? Scalar product. Okay, let's calculate the scalar product, alright? F sub x times dx dt, and I want bigger font, plus f sub y dy dt is equal to 0. And then of course we can do some algebra using the chain rule. As a matter of fact, we can flip these to the other side, and the other side, wait a minute, that's 0. So what do you get? We get this. We get this out, this out. All right? So compare this with the original equation, original exact equation here, m dx plus n dy. What conclusion do we get? I get m is f sub x and n is f sub y. That's what I'm getting. Compare this and that, and this and that. Okay, we're almost there. Now, in order to make this thing work, m sub y is equal to f sub x, and then take the derivative by y again. But then again, it does not matter whether you take the derivative by y first and x later. And that is n sub x. So these two are always the same, and that's why m sub y and n sub x are equal. Tracing back, if so, then you will be able to find out appropriate capital F so that you're going to get an implicit solution like this. That's how things are connected. And deep down, the core portion of this analysis is a chain rule.